So hi everyone. So my title here is a little bit different from the one listed on the agenda, which says 2012 to 2014 California drought. So the drought, so California was pretty dry in the winter of 2012 to 13, but it was actually not that exceptional. So here we mainly focus on the drought that happened last year, and we will further talk about this issue in the presentation. So we all know that California experienced very severe drought last winter. In California, water resources are almost all about snow. So its spring runoff is mostly generated from the snow melt from the mountainous areas, which is mainly accumulated from winter precipitation. So this is a map of snowpack on April the 1st this year. We can see that California had a much below normal snowpack last winter. And then California drought was very severe last year, and there are a lot of newspaper articles talking about this issue. So the severity of California drought last year is of no doubt, but the causes of this event are still under debate. Some people link this extreme drought event to the climate change, while some others simply argue that it might be a result of natural variability. So which one of these is closer to the truth? We try to answer this question from a hydrologic perspective. So in our study, we focus on the area of Sierra Nevada mountain range area where the long-term simulated April 1 snowpack is larger than 10 millimeters. And all of our following analyses are all based on this blue area here. And our period of analysis is 1920 to 2014, which covers 95 years of record. And then the data sets we used in the study are first the meteorological forcing data, including daily precipitation and temperature. These two data are extracted from University of Washington Drought Monitor System, and they're station-based data sets at 116-degree spatial resolution. And then for snow water equivalent, SWE, and runoff, because we don't have these data back into history. So what we did was that we ran the variable infiltration capacity model, the VIC model, to simulate these two variables. The VIC model basically takes the meteorological forcing data as input and simulates hydrological processes and output hydrologic variables. And it has been successfully used in many large basins and areas. So in our study, we focus on answering three questions. The first question is, how has the climate actually changed in California? So to do this, we first aggregate the accumulated winter precipitation in each year over the entire study area. So we got one single value for each year. And then for the time series of the 95 years, we carried out Mercandle test and sand slope estimator to detect the significance and the magnitude of long-term trend. So here, we can see that there's actually no significant long-term trend in winter precipitation, but there are lots of variability. And then for average winter temperature, there is an increasing trend, which is about 0.4 degrees Celsius per 100 years. And then for April 1 snowpack, there's a decreasing trend. So this lets us think that the increasing trend in temperature might be a cause of the decreasing trend in SWE. And we will further prove this point later in the presentation. And then similarly for spring runoff, it has a decreasing trend because the runoff is mostly generated from snow melt. Okay, so our second question to answer is, how dry was California last year? And we want to quantify this using frequency analysis. So basically, we plot historical winter precipitation in each year on the plot according to plotting position method. And then the higher the return period, it means that the less frequent the low precipitation event would happen, so the more severe the drought is. And the red dot here is the water year 2014, which is last winter. And we can see that last winter had the third lowest winter precipitation in the 95 years of record. So last year was pretty dry, but it was not the worst. 1977 had the lowest winter precipitation in the whole record, and 1976 was also a very dry year. So notice that 1976 and 1977 are both exceptionally dry in terms of precipitation, and the drought lasted for 2 years. But in contrast, the water year 2013 was actually not that exceptionally dry in the historical context. And then we did the same analysis for April 1 snowpack. And again, 2014 had the second lowest SWE in the record, and 1977 had the lowest, and 1976 is also among the 5 driest years in terms of SWE. And the same thing for spring runoff, and the results are also very similar. So now we have already looked at the climate change and the severity of the drought last year. So our third and the key question here is that, is there actually a link between these two? So to answer this question, we first carried out a simple correlation analysis. So this is April 1 SWE versus winter precipitation. We can see a very strong positive correlation between these two, which is very reasonable. And then if we mark out the 5 years with the lowest SWE, we can see that they're all located at the very low end of winter precipitation. But for SWE versus winter temperature, we can see a vague negative relationship, but the correlation is much weaker than that of SWE versus winter precipitation. And for the 5 years with the lowest SWE, they generally happened in warmer winters, but for example, let's say 1977, which is the driest year in the record, its winter temperature is actually around median value, and similar for 1976 and 2007. So this tells us that warmer winters might have something to do with lower SWE, but really the winter precipitation is the main control of snowpack. But recall that winter precipitation doesn't have a long-term trend, but lots of variability. So this leads us to think that the variability in winter precipitation might also be the main cause of drought events. So to further support this argument, we did the second analysis, detrended temperature scenarios. So in addition to the base scenario that we have already talked about, we removed the increasing trend in our temperature data, and then used the hydrologic model to simulate the hydrological conditions without climate change. So for example, if the black line here is the temperature data, then we remove the long-term trend in the temperature in 2 ways. The first way is to remove the trend to the beginning of the record, so we got a cold scenario. And the second way is to remove it to the end of the record, so we obtain the warm scenario. And then for both of the 2 scenarios, the long-term trend is removed, but the daily variation is preserved. So let's see what would happen to snowpack if there is no warming trend. So it's a little bit hard to see here from the plot, but after the warming trend is removed, the original decreasing trend in snowpack also disappeared. So this strongly suggests that the warming trend is the main cause of the decreasing trend in SWE. So this conclusion is also consistent with many previous studies. And again, we did frequency analysis for the 2 virtual scenarios. We can see that after we remove the warming trend, the rank of the water year 2014 would go up a little bit, but it would still be among the 5 driest years in the record, and similar for the other extreme dry years. So this tells us that the warming trend actually only has little impact on the extreme drought events. But notice that after we remove the warming trend, the magnitude of the drought event last year would only change a little bit, but actually the return period of it would obviously decrease because of the very flat shape here at the end of these curves. And another interesting thing to notice on the plot is that the 3 curves diverge as the SWE goes up, which means that the warming effects are larger in wetter years. And we did the same analysis for spring runoff, and again, the warming trend seems to only have very little impact on the extreme drought events, but its impact seems to be larger as the runoff goes up. So based on all of our analysis, did climate change cause the decreasing trends in snowpack and spring runoff? Yes, probably, but is it also the main cause of the more severe droughts? Our answer is not so much. So to conclude our study, there are lots of natural variability in the record. Snowpack is primarily correlated with winter precipitation, secondarily with winter temperature. But winter precipitation doesn't have a long-term trend, but lots of variability. The warming climate does not affect extreme drought events too much. So our main argument here is that climate change might have slightly exacerbated the 2014 drought because the warming climate might have caused more warmer winters. But these kinds of extreme drought events in the Sierra Nevada area in California are mainly due to the natural variability in precipitation. Yeah, that's it. Thank you very much.
Hi, we have time for a question or two.
Mm-hmm. Yeah.
Temperature or climate plays a differential role without transpiration.
We didn't really look at the evapotranspiration specifically in our study, but as I mentioned before, so in California, evapotranspiration or other hydrologic variables are not as important as snowpack because of the special geographical location of California. So most of the water resources are from snowmelt. So in our study, we just mostly look at the snowpack and the runoff. Did it answer your question?
I mean, I would agree that evapotranspiration isn't a water source, but so I mean, if there's a lot of evapotranspiration, equal water resources that are snow freezing, the impact on drought is going to be a lot heavier than if there's less evapotranspiration. So you guys are
Yeah.
evapotranspiration. It's hard to assess the answer to your primary question.
So here we didn't look at the ET variable specifically, but we did analyze. So I think temperature would be the main effect on the change of ET. So what we did was that we look at temperature. So we also look at like if we don't have the trend in temperature, then what would happen to the drought? So I think if there's no temperature trend, the ET change should be not very big. But we didn't really look at the variable specifically, yeah.
Thank you.
Okay, thank you.
Thanks.